Welcome to the 2020 Beno Gutenberg Lecture of the Seismology section of AGU. My name is Ann Sheehan, and I'm the current president of the Seismology section. As is tradition, before we introduce our Gutenberg lecturer, Malcolm Sambridge, we'll take a few minutes to congratulate our seismology honorees and award winners, both at the union and section levels, and thank our volunteers and donors. We're pleased to announce the newly elected officers of the Seismology section. These are Martha Savage, who was elected president-elect, and Colleen Dalton, who was elected secretary. Suzanne Vanderlee, our current president-elect, will step into the president role next year. I'd next like to thank Mr. Jerry Peros for his generosity in supporting the new Jerome M. Peros Scholarships in Geophysical Instrumentation. These scholarships support graduate students with a demonstrated interest in geophysical instrumentation and precise field measurements in seismology, atmospheric sciences, or ocean sciences. The scholarship is awarded to 3 students each year to help build a solid talent pool working on and interested in geophysical instrumentation. Jerome Peros is president of Peros Scientific. Thank you for your generosity.
Hi, I'm Jerry Peros, and I'm the sponsor of the Peros Scholarship Awards in Geophysical Instrumentation. The scientists at AGU have made great contributions to science, education, and public safety. We're happy to support future generations of scientists with the Peros Scholarships in Geophysical Instrumentation. Precision measurements are the fundamental basis of experimental science. Commercial applications of experimental science drive the technological and economic progress for our society. Natural disasters have caused the deaths of hundreds of thousands of people worldwide, with associated costs of hundreds of billions of dollars in property damage. Now, disaster warning systems depend on sensors that measure the pressure and seismic signals associated with tsunamis, earthquakes, and severe weather. Those sensor signals need to be transmitted, analyzed, evaluated, and communicated to the public to take protective actions. These important tasks are fulfilled by you and your colleagues at AGU. I congratulate this year's recipients of the Peros Scholarship Awards and thank the heads of the atmospheric, oceanic, and seismology sections for their wise selection. We wish you well in your careers and look forward to your contributions to science, education, and general society. Please stay well.
We are proud to recognize and congratulate our 2020 union medalists and members elected into the 2020 class of fellows. This year's AGU Thinking Layman Medal has been awarded to Peter Shearer. The Walter Booker Medal winner is Susan Beck, and Brandon Schmidt is a recipient of the James B. McElroy. 4 seismology members were also elected to the 2020 class of fellows: Rachel Abercrombie, Larry Brown, Terboya Kalchich, and Jean-Paul Guerrero. Congratulations. At this point, I would like to recognize our Seismology section awards. First, the Kayaki Early Career Award, which is presented annually to an early career scientist in recognition of their scientific accomplishments in the field of seismology. The award, which was established in 2008, honors the life and work of Kayaki. Our recipient this year is Wei-Sen Shen of Stony Brook University. Wei-Sen's main research interests are seismic imaging of the crust and mantle lithosphere and interpreting these images to address questions about the formation and evolution of continents. Professor Shen has developed new approaches for seismic imaging that allow joint inversion of observations of high-frequency scattered body waves and low-frequency surface waves. Importantly, his use of Bayesian statistics allows meaningful uncertainties to be assigned to his models, which has not historically been possible. Congratulations, Wei-Sen. I invite you to share a few comments with our community.
It is my great honor to receive the 2020 Aki Award. and I want to thank the seismology session of AGU for this tremendous encouragement. This honor would not happen to me without the extraordinary mentorship that I was given by my PhD advisor, Michael Rieswolder, who taught me the significance of uncertainties at the University of Colorado. And I also want to acknowledge Douglas Wings, who broadens my vision during my postdoc time at Washington University in St. Louis. And over the past several years, I was given tremendous support from a long list of friends, colleagues, and family members, as well as from Stony Brook University. For young scientists, there is this very unique character in the field of seismology. This character is exemplified by individuals like Kayaki, by groups who work in the field to collect the data and share with the community, by programs like EarthScope and POLEnet, and by facilities like IRIS. And this is a character of inclusiveness and unselfishness. Because of this character, young people like me are given equal and free access to the seismic data across the globe, which is the most important ingredients in all observational seismology research. So I want to take this chance to join the previous awardees to cherish this character of inclusiveness and unselfishness, which cannot be overemphasized in the year of 2020. Finally, there is no question that those models that I have produced so far are wrong. But perhaps some of them are useful. And this award will provide a lot of encouragement for me to jump out of my comfort zone to make more useful models in the future. Thank you.
Thank you for inviting me to introduce the Paul G. Silver Award in my husband's honor and memory. It is a great honor for me to be here today, even virtually, to celebrate both Paul's legacy and the achievement of this year's two awardees, Dr. Doug Toomey and Dr. Ramon R. Smith. Some of you may know Paul Silver through his work on slow earthquakes, earthquake precursors, impact of earthquake on geyser eruptions, but most of all on his work on anisotropy. However, many of you may not have had a chance to meet him in person. Paul was curious. He needed to know the why, how, when, where in all things. And this was a bit difficult for our two daughters when they were growing up. This curiosity was complemented by other character traits: creativity, enthusiasm, and selfishness. He was a hardworking and dedicated scientist, and most of all, a fun person, never boring. He had an infectious mind that could brighten any gray day or loosen any tense situation. But most of all, he loved working with young scientists. And from what I was told, he was a great mentor. He loved sharing his enthusiasm and love of science, discussing and vigorously debating his ideas with all his collaborators, using the critics to refine or correct his ideas. He was unpretentious and perseverant. He was not stopped by any setbacks, but worked harder to move forward. A native of California, he knew the devastating impact of earthquakes and the need to better know the processes that led to earthquake if we want one day to be able to predict them. That is what guided him in the conception, advocacy, and creation of the Plate Boundary Observatory, or PBO. He worked tirelessly to find the best solution for the majority of those involved and to advance the knowledge of the Earth's functioning. So today, it's a great honor to bestow the award in his name to scientists who, as we will hear from Julia Morgan and from Anne Sheehan, demonstrated the same quality of unselfish leadership and creativity in service of the whole scientific community. Thank you.
I would like to honor the recipients of the Paul G. Silver Award for Outstanding Scientific Service, which recognizes significant contributions to the fields of geodesy, seismology, or tectonophysics for their mentorship of early career scientists, leadership on community research initiatives, or other collaborative research efforts. We have two recipients this year, Ramon Aerosmith, who who was honored during the introduction to the Birch Lecture, and Doug Toomey, who will be recognized here. Douglas Toomey from the University of Oregon receives a Paul Silver Award in recognition of his leadership with planning and implementing the Cascadia Initiative Ocean Bottom Seismometer Community Experiment. This experiment transformed the way the seismic community collects large marine data sets for passive seismology, enabling an experiment of unprecedented scope, provided numerous students and early career scientists with experience in seagoing seismic data acquisition and an opportunity to conduct research on open and unopen access data set, and is a template that has informed more recent community experiments and planning activities. Doug's leadership was pivotal to its success, and he is a highly deserving recipient of the Paul G. Silver Award for outstanding scientific service. Congratulations, Doug, and I invite you to share a few words with our community.
Thank you, Natalie, for recalling Paul's enthusiasm for a full, rich life that is an inspiration for our better selves. And thank you, Anne, for that kind citation. It is a heartfelt honor to receive the Paul G. Silver Award for outstanding scientific service from the tectonophysics, seismology, and geodesy sections of AGU. The Cascadia Initiative was an ambitious experiment and a resounding success because of the community. Elder statesmen, including Don Forsyth and John Delaney, provided sage advice and admired role models. At NSF, the deft leadership and opportunism of Bob Dietrich, Rodi Batiza, and Rick Carlson seized the opportunity of ARA stimulus funding to launch the Cascadia Initiative. The Cascadia Initiative benefited from the intelligence, camaraderie, and selfless can-do attitude of the Cascadia Initiative expedition team, namely Richard Allen, John Collins, Robert Ziak, Emily Hoft, Dean Livelybrooks, Jeff McGuire, Susan Swartz, Maya Tolstoy, Anne Trehu, and William Wilcock. One of the great rewards of a scientific career is to work with the best, and to see it was exactly that. Any seagoing activity is an exercise in failing forward. Over 5 years and 25 cruises, we had the ship's crew to bring expeditions home safely and successfully, and the expertise of the Woods Hole, Lamont, and Scripps ocean bottom seismology teams to ensure that the ratio of good to bad data was in our favor. Lastly, I want to provide forward-looking advice to the individuals that contributed and are still contributing to the legacy of the Cascadia Initiative, the early career scientists who became marine seismologists, made impactful discoveries, and promoted their work. My advice is this: have bold visions, design ambitious community-centered experiments with open access to data, and reap the benefits of how a rising tide of communal success can lift all boats.
Finally, it's time to introduce our 2020 Gutenberg Lecture. I'm pleased to introduce the 2020 AGU Seismology Section Beno Gutenberg Lecturer, Dr. Malcolm Sambridge from the Australian National University. These highly innovative developments in inversion have shaped seismological practice and influenced many other branches of the geosciences. Some of his largest contributions to seismology have been in the development of various Monte Carlo methods for the solution of nonlinear inference problems in the earth sciences. In addition to the methods themselves, he's demonstrated their ability to solve problems that were not solvable before, at least not without taking serious simplifications. Prominent examples include the neighborhood algorithm, genetic algorithms, and transdimensional tomography. Throughout his work, Malcolm has developed the tools necessary to estimate uncertainty and has made them accessible to others, for example, by developing and disseminating software. Many researchers have used his codes to solve problems that otherwise would have been almost intractable. It is noteworthy that Malcolm is also a scientist and teacher of wide-ranging interests and achievements, spreading to other scientific disciplines. Now I invite you to enjoy Dr. Sambridge's presentation, a biased tour of geophysical inversion, and we hope to see you at the live question and answer session immediately following the lecture.
Dear American Geophysical Union members and associates, dear colleagues, friends, and guests, Welcome to the 2020 Gutenberg Lecture from the Australian Academy of Sciences' beautiful Shine Dome in Canberra, the nation's capital. This year's recipient of the Gutenberg Lecture is Professor Malcolm Sambridge. The lecture itself is presented annually in recognition of the outstanding contributions to the field of seismology. And I'm Hrvoje Tkalčić, one of Malcolm's colleagues from the Australian National University, and it's my great honor and pleasure to introduce Malcolm to you today. So Malcolm comes originally from the United Kingdom, and his educational background is in physics and mathematics. He received his PhD in geophysics in 1988 from the Australian National University, and he was then a fellow in the Carnegie Institute of Washington between 1988 and 1989. Subsequently, he was a research associate at the University of Cambridge between 1989 and 1992, the year he returned to Research School of Earth Sciences at the Australian National University. And here, as you all know, he has had a fruitful academic career with nearly 150 international peer-reviewed papers. So Malcolm, before I go any further, I would say that among other recognitions, he received the Prize Medal from the Royal Astronomical Society, London, in 2009. He was elected an AGU Fellow in 2010, elected a Fellow of the Australian Academy of Science in 2015, and last but not least, he, apart from this Gutenberg Lecture, he is the recipient of the 2021 Beno Gutenberg Medal that is awarded by the European Geosciences Union. Malcolm is among the leading mathematical geophysicists in the world. His innovative contributions to inverse theory, most notably Monte Carlo methods, but apart from Monte Carlo methods, as I'm sure you will see in this lecture, other innovative methods have really shaped the field of seismology and influenced other disciplines. And not just through his outstanding research contributions, but also through his willingness to share knowledge and methods through an open source software, through his drive to educate youngsters in his leadership role in the Seismometers in Schools initiative. He has made a significant and long-term impact. So for all that he has done, he is an incredibly well-deserving recipient of this award. So Malcolm, please give a warm welcome to Malcolm.
So, thank you very much, Hrvoje, and thank you all for coming along today on this beautiful Thursday summer day in Canberra. So, the title of my talk today has two important words in it: bias and tour. It's a biased tour, and a tour is not complete without, let's see if it works, tour guides. Now, it's appropriate at this sort of time to acknowledge one's own tour guides, and these are all people that I've benefited from very much over the years, who have taught me and helped me along the way. I won't tell a story about each of them because it will be taken up the whole time of the lecture. But at the bottom there are some particular people who have contributed directly to this talk: Matthias, Busa and Andrew, who are in the audience. The most recent slide came in at 12:01 today, and it made it into the talk. So thank you, Matthias, for that one. And while we're doing our thanks, let's thank our sponsors. We have to thank our sponsors for various organisations, the ANU, CSIRO, Audscope, Geoscience Australia, the Australian Research Council, all have contributed funding or in-kind support for infrastructure or research in one way or another, the things you're hearing about today. And one that you would not be familiar with necessarily is InLab, which is a new venture, collaborative venture between CSIRO and ANU that we've just started, and they're supporting the drinks later, so we've got to acknowledge them too. This lecture is named after Beno Gutenberg, and here's a picture given to me by Andrew and Brian. It came out of a discussion where Beno Gutenberg is the person highlighted in the figure. This is 1929 photo taken at the Caltech World Authorities at the Seismo Lab, and there are some absolutely ground-shaking names of people in this. There's Gutenberg, as you see, Benioff to his right, there's Charles Richter in there, Wood and Anderson, Harry Reid, Arthur Day, but the person directly to the left of Beno Gutenberg is Sir Harold Jeffreys, and by way of a connection, Harold Jeffreys connects to my own lineage, of an academic lineage. He would be technically my great-grandfather from academic terms, and is also connected to Andrew and Brian, so we keep it all in the family. But anyway, there's Beno Gutenberg. Now, the title of the talk is A Biased Tour. Now, biased meaning having a preference for one thing over another, and I'll certainly have that, because this is not intended to be an unbiased, balanced review of geophysical inversion. It's very much a bias because it's my outlook. And it's a tour in that we'll be stopping by a number of places, not for very long, but we will visit them. And in doing so, it's also an AGU talk, and everyone knows that you write an abstract for AGU, and your talk doesn't necessarily correspond to your abstract. So my prior was to talk about the past and the present of geophysical inversion, but actually what I'm going to talk about is the present and what I see as the future, my biased view of the future. And indeed, this talk is really aimed at students and postdocs, because it is some seeds of ideas that I think that will be influential or potentially influential in the future of geophysical inversion. Now, it's a dynamic talk, at least in one way, which is that there's a website with everything you can see here today, all animations on that website. Thank you, Andrew. And the idea is that you can give some feedback. If you don't ask a question now, you can ask one later. You can complain. You can say, that was very biased. You can engage. And the idea is to sort of create that dynamism. So please give some feedback. Agree, disagree. Suggest some ideas. Okay, so inverse problems is something I've studied for a long time, had a lot of interest in, and they come in all shapes and sizes. From geoscientists are often looking at inverse problems in the sense of we have indirect information about the Earth. Yeah? Most of us live on the Earth, and we measure on and above the Earth, and we're interested in things that happen at depth or sometimes even in the past. So seismic imaging, using seismology to look at the Earth's interior at small scale lengths there, refraction seismology used for exploration geophysics, airborne geophysics. We've got Russ Brody in the audience, who's an expert on airborne AEM. We have airborne geophysics, and even new styles of inverse problem. This is a slide from Rodri Davies, which is trying to look at the thermochemical history of the Earth, bringing together multiple strands of information, including geophysical and geochemical. So all shapes and sizes, but I can't pop this slide up without reminding people my favourite quote from Samuel Carlin, that the purpose of models is not to fit the data, but to sharpen the questions. Yet, we mainly build models. The purpose is actually to try and create understanding of the Earth. Now, here's some very famous pictures of people who have created models. Over 30 years of seismic imaging, from the ones on the top left here, the sort of classic papers by Zawonsky and Woodhouse, who brought together a number of earlier studies, producing the really first generation of seismic image of the whole Earth. Very long wavelength, and in the day then, it was sort of 2,000 surface wave seismograms, 1,500 body wave seismograms, and 870 source receiver pairs. Fast forward 30 years, and this topic has moved on to something like Ebru Bodzag's here work on the very first generation of global tomographic model from adjoint tomography, where they're now using 1.2 to 3.8 million pieces of data and taking something like 1.6 million CPU hours to create these 15 iterations of this model here. So enormous changes in data volumes and computational resources. But there's one thing that hasn't really changed between this study and this study, and that's how we fit our data, how we define the objective of an inversion. Typically, we're doing some sort of minimization of squares of residuals, a least squares approach. And it's appropriate in this type of problem, and really it has not changed very much, even though the style and the process changed dramatically over 30 years. So, today I'm going to be talking about things that challenge that notion of least squares and pointing out a few other ideas that I think are very valuable that could be useful in the future. Now, here's a topic I've talked about before, compressed sensing, and it's really by way of introduction to the next few slides. So compressed sensing is a field that really has its origins about 15 years ago in the work of Kanders and Donahoe and company, mathematical scientists, and they found that you can irregularly sample data, in short, and reconstruct it exactly using an inverse method under very special conditions, but still reasonably general. And the idea is that rather than collecting uniform data that we do regularly, collect it irregularly, and provided certain conditions that we won't go into are satisfied, you can reconstruct data exactly. And their idea was, well, don't collect all the data, collect it irregularly and combine it with mathematical optimization and call that your data collection. And in doing so, you can vastly reduce the amount of storage and increase the bandwidth of data, essentially better forms of data collection. And Felix Herrmann's really been the leader of this in the geosciences, and he's convinced oil companies to sort of invest in this type of technology. And because you can do that in time series, you can also do it with images. There's an image by Escher, where it's been sampled at roughly 10% and reconstructed in a sparse sense. Now, the reason I put this up here is that it's an example of sparse inversion. In fact, it's a little gem that is missing. It was previously missing in geophysical inversion, that if you've got a problem that fits into this, that is basically an empty model, you can reconstruct it exactly or very accurately using this idea of sparsity. Now, that's all well and good. A lot of geophysicists have used that idea to try and reconstruct Earth models using seismic imaging. Now, the problem is the Earth isn't necessarily sparse. Yeah? So the question is, how do you use this technology when you don't necessarily satisfy the correct conditions, which is having a representation of the Earth in such a way that only a few of the unknowns are non-zero and everything else is zero? Well, here's an example of a single pixel model. The simplest possible example I can think of, you add these 3 pixels together, you get a sparse model like this. So the theory says that you can reconstruct models like this, which are trivially simple, very accurately, because this is sparse. But this one here is also sparse. It's sparse in a different sense, a sense of a discrete cosine model. So both of these models, the theory can be applied to. But what it cannot yet be applied to is if you combine them and look at a model which perhaps has long wavelength structure, which is a smooth background here, and local structure. And that's the situation we're offering in seismology. We might have a long wavelength mantle structure, and we think we have fine scale structure in a subduction zone or near a volcanic zone or in a small region. And the idea of over-complete tomography, which is the PhD work of Busa here, co-supervised with Andrew, is to say, can we extend these ideas to problems of this type, where given a certain number of data, can we exploit these ideas where the problem isn't sparse, but it's sparse in two bases? Can we combine them together? And it's not obvious from the maths that you can. And it turns out, I'll show you some examples now. Here's what we're going to show you is a complex figure. We're going to have a number of rays here, some experiments from Busa. Here's going to be the reconstructed over-complete model. Here's going to be the error in the model. It's a very simple case where we know, a synthetic case where we know the error. So this is the error in the model. This is going to be the least squares solution with some sort of damping here, squared, and this is the error in the least squared. So this is also in the same parameterization. It's exactly the same parameter. The only thing we're changing is the sparsity. This model isn't sparse, but we're going to hope and try and make the sparsity idea pick out the correct two subsparses. That's the idea. And we're going to show a movie, and on the right-hand side, you're going to see the fit to the model, the closeness of the model here. The red line's going to be the least squares. The black one's going to be the sparse solution. So thank you, Bisa. I'm going to play this here. And what you see is, boof, okay? That cliff you see is classically what you see in a compressed sensing environment. And as we reach that cliff, if anyone was noticing, this model becomes almost exact, and the least squares toddles on until there's enough data to get better and better and better. Now, that's exactly what we hope to see in this case, because it shows that you can utilize this sparse idea and the accuracy of it in problems that are not actually sparse. So it's an extension of that, and we're calling that over-complete tomography. Okay, so that is an idea that uses non-least squares to try and recover Earth models. And we think there are a number of different applications to this, problems that have structure on more than one scale. Now, we're moving on very swiftly from our brief visit to over-complete tomography to machine learning. Now, I've heard lots about machine learning. The number of sessions on machine learning growing at AGU is itself growing greater than linear. Now, here's the audience participation side. This is a slide from Valentine and Trompere, and we have 4 wiggles. And given there are lots of seismologists in the audience, the question is, which one's the seismogram? Who votes for the first? Second? Third? Fourth? Fourth, yes. The fourth is the seismogram. The first, of course, is the stock price. The second one is the temperature in Birmingham. I don't know what that scale is, but I think it's cold all the time there. White noise is the third one, and the fourth one is a seismogram. Now, the very point that most of you, in fact, all of you, I think Andrew got it wrong, all of you get that right, is that you have a model in your head of what a seismogram looks like. You can look at each of those and compare it to the model in your head. You're acting as a misfit function. Yeah? You've done an optimization, you've picked out the correct one. And the whole concept of machine learning is, can we capture that idea of pattern recognition that's in your head and put it into a computer and use it to drive inversion? And I think the answer emerging is yes. So this is the work of Matthias, a PhD student in the group, and he's exploited this concept of what we call a GAN. And the GAN is a standard idea from machine learning. It is essentially the competition between two things. One thing which generates dots or models in a parameter space, unknowns. These are your unknowns. This thing will generate random unknowns. And this thing over here, called the discriminator, will try and tell you whether the data from those unknowns, those models, is good or bad. And by saying that, it sees the real data and it tells this guy, I've beaten you. I can tell your predictions from your models look nothing like the data, just like you did with the 4 wiggles previously. And the idea is the competition between these two drives this guy to get better and better and better and get models that fit the data better and better and better. So it is a competition that drives the solution. And that's the main concept here that I think is very interesting. And I'm going to show you a little example of where that could be useful from Matthias's work. So here, again, a toy trivial example to show the ideas. Given the mass of the Earth, what's the density of the core and what's the radius of the core, or an idealized ball? Here's the answer. Given the mass, how it depends upon two different solid bodies in this case. So we want to find the radius of the core and the density of the core, and to do that, it's a completely underdetermined problem. We only have one piece of data. We have the mass of the Earth in this case is 16 units. And as that line goes up and down here, all of those models, an infinite number of them, fit the data equally well. Yeah? So we cannot determine, in this toy problem, the radius and the mass, the radius and the density from the mass. So we have a very nonlinear problem. It turns out we have a nonlinear problem because this is quite complex. It's not a simple Gaussian. It's a nonlinear problem. It's underdetermined, and it's the simplest possible one I can think of with one parameter. So we're going to use that as a toy. Now, what I'm going to show you here is one application of a GAN to this problem. On the left-hand side, you see a set of samples in a model space. So this is the core radius, this is the core density. Now, these have been produced by a standard Bayesian sampling, Markov chain Monte Carlo. If that means something to you, it will mean something to a lot of people in the audience. And on the right-hand side, we're going to say, this is our data for our problem. This is actually the data. And we're going to say, can we train a neural network to reproduce that distribution? Can we do that? Because if we can, it's very useful because, well, we could use this forevermore. Rather than using very expensive Markov chain Monte Carlo, or even storing all the results, we can replace the result with a trained GAN that can generate rapidly millions or trillions of possible solutions that mimic the result of a Bayesian sampling. So if we can do that, it's a good thing and it's immediately useful. And here's a simple example of trying to do that. So I'm going to play these are the samples of the GAN as it trains itself against the data. And hopefully you'll see that the red dots, after a period of time, learn and find the distribution of the black dots. And the idea is that once it's trained itself, we can then use that to sample problems or to calculate uncertainties or anything you want in a standard Bayesian approach. And I think you see there that that worked. The red dots sort of fly off and then they gradually sample the right structure. And in this problem, it's only 2 parameters, but you get the idea that the GAN can train and reproduce the Markov chain. But this is extremely rapid. It requires no more complicated physics. I mean, a neural network is very, very simple. Yeah. So once we've trained our GAN, we can use that. We don't really have to store, in this case, it's simple, but if we try, and the biggest problem, if anyone has done Markov chain Monte Carlo, is A, when does it ever end? There's an old story that you run it, you do your best job, you write your paper, you submit your paper, and then you press the button and start your Monte Carlo again, and when the reviews come back from your paper, you stop the calculation, and you've got all the results, all the answers to the reviewer's questions in the calculation you've just done. But with a GAN, we don't need to do that anymore, because if we can train GANs for general problems, we can replace the output of a Monte Carlo, and we can use them for other purposes. Okay, so the final area that I'm going to visit, and it's going to be for the remainder of this talk, is to be talking about an alternative idea that I think is going to be important in geophysical inversion. And again, it's an idea that we've borrowed from somewhere else. Brian Kennett always used to tell me that if you steal from one person, that's plagiarism. And if you steal from many, that's research. And that's what we're doing here. We're stealing from other fields. We're borrowing. And that's how science progresses. Okay, so this field is called optimal transport. And some of you would have heard about it because there have been, and I'll come across this in a minute, a number of papers in the geosciences that have made use of this. Certainly, I am nowhere near the first. I'm about 8 years late. but we're going to have some fun and look at this idea. Okay, so here you might recognize the symbols. Optimal transport comes from the 19th century. There have been 2 Fields Medals in this topic and 1 Nobel Prize since then, often on the mathematics of it. The Nobel Prize is actually in economics. That's where the mathematicians get their Nobel Prizes. On the left-hand side is an apple. I'm going to turn the apple into an orange. I'm not going to show you the maths. I'm just going to show you some animations. An apple becomes an orange. And in the middle, I'm going to turn the apple into an orange with optimal transport. Now, on the left-hand side, I'm going to use linear. So the image you see is just going to be a weighted sum of the apple and an orange. And that actually is closely connected to least squares. In fact, it is the analog of least squares in here. So let's do that. And you can see what's going to happen. The green's going to fade away, and the orange will come into view. Okay? And what's happening there is really there's no connection between the 2 images, yeah? One's just going to 0, and the other one's going from 0 to maximum. Optimal transport, however, behaves rather differently. Here's the apple turning into the orange using optimal transport. Okay? There's a little bit of graphical going back in again. And really the only thing I want you to capture from here is that optimal transport is not about one image fading and another one coming back. It's about using the character of the image and transforming it in some smooth way into another image. In fact, you can do this between any 2 images. George Bush, Bill Clinton, whatever you want. Here it's very simple. Now, the reason that this is useful is that if you have a measure of way of changing A into B, you effectively have a measure of how far A is from B. And if you can tell the difference, a distance between A and B, A could be our observed seismogram and B could be our predicted seismogram, or A could be any bit of data you want to fit. There will be restrictions, and B could be your prediction from your geophysics model or your physical model. So this provides a new way of minimizing and defining inverse problems, all which depend upon a distance measure between 2 things. Okay, so I said waveforms. Here's exactly the same thing transformed into a waveform space. At the top is the linear case. So we're moving from a blue waveform to a black waveform. And the top one, you'll see, if you look at that, all that's happening is the amplitudes of one are going down and the amplitudes of the others are going up. So least squares fitting is exactly corresponds to least squares fitting, which only looks at the differences in the heights of the 2 wiggles. On the bottom, hopefully you see the mass of one wiggle going into the mass of the other wiggle. We could think of this as a pile of sand that starts off here, a shape of a whole set of pile of sands, and they move over to a set of sand piles over here on the beach. Yeah? It's moving in position and in amplitude, and that's the key thing of optimal transport, that you're not just moving in amplitude, as the top one is, we're moving in position and amplitude. Now, I haven't described how you do this, and I'll briefly skip over it, but the distance measure between where we start and where we end in this context is called the Wasserstein Distance. And the Wasserstein Distance is, if we think of the piles of sand, it's very simple. It's just the mass of the sand times the distance we move each parcel of sand. To generalize that, I can put the distance to a power, and we define the pth Wasserstein distance as the mass times the distance to the power of p. So the mass in this case would be like the area under the curve, and we're moving it over. Now, the whole point of optimal transport is that you do that in an optimal, it's got the word optimal in it, so what is optimized? What is optimized is, here's my starting wiggle here, that's f of x, my target is g of x, and transforming f of x exactly to g of x, I form what we call a transport plan, which is just really the recipe of how much of each parcel you move from one to the other. And what's minimized, or what's optimal, is this distance, Wasserstein distance. the distance times the mass, or the mass times the distance to a power. And Kantorovich in 1942 was the one who first explained this in these terms. In fact, he converted the original ideas of Monge from the 19th century to problems that actually can be solved. It wasn't really clear when this problem was first posed that there was a mathematical solution to it. And Kantorovich reformulated it into a way where it was guaranteed to have a solution. And it comes down to just simple linear programming. Ideal, because in the 1940s and 50s, linear programming took off, especially where optimizing of factories and behaviors and constrained optimization really was in its heyday in the 40s and 50s. And he showed that this was just an example of that problem. So great, we already know how to solve these problems. Unfortunately, there's a catch. And the catch is that this, while being simple and foolproof and working for any case, is extremely computationally expensive to do this for big problems. And so the whole game has been really finding different, more efficient, practical ways of solving this problem and not using linear programming. But nevertheless, this works. So we have this concept of a transport plan and moving from one source to a target. And in doing that, we find the minimal distance, which is the Wasserstein distance. Okay, so I'm moving along to bringing this back to geoscience. Here are all of the authors, probably not all of the authors, some of the authors who have been responsible for bringing this topic into the geosciences. Bjorn Enquist and company were the first to introduce it for exploration seismology, full waveform inversion in searching for oil and minerals, etc., or at least from seismic reflectivity, essentially. Metivier, the Grenoble group here, have made some wonderful contributions to this field, really taking a different approach to Enquist in terms of the computation, but the same type of problem to be solved. And there have been a number of very recent papers exploring this idea, Hedajian and Huang in gravity inversion and seismic receiver function. But really, I'd still say this topic is in its infancy, and it's a wide open space. Because each of these studies take different approaches to how you find this distance, how you solve this math problem. And particularly, one thing I've glossed over is that really optimal transport is applied to probability distributions. It's actually not transferring a wiggle to a wiggle, but really a probability distribution into another, which is really a positive function that just integrates to one. A curve, much like you saw on the previous slide here. A curve into another curve, or a surface into a surface, or a volume into a volume. But it has to be positive. And most seismograms are not positive, of course. So how do you turn a seismogram or a general thing you might want to fit into something that you can use this on? Because it only works for positive functions or particularly probability distributions. So different people have taken different methods. Now, before I go and summarize these very, very briefly, I'm going to describe now a new approach to this whole thing that Andy Jackson and Andrew Valentine and I have been taking, working on for the last sort of year or so. It's still a work in progress. And the point I want to make is that these problems are extremely difficult to solve, but actually in one dimension, they're trivial to solve. In fact, Viliani, who won the Fields Medal, pointed out, and everyone knows this, that there was an analytical solution to this problem in 1D. So if you've got a one-dimensional PDF into a one-dimensional PDF, you can solve it exactly. You don't need to do optimization. You don't need to solve a differential equation. And it turns out that if you look through the theory, and that's what we've done here, it turns out that this Wasserstein distance is just beautifully the dot product of two terms. I can dot product two vectors. The two vectors you need to dot product themselves require a sort. So for the computational scientists in the room, it's a sort plus a dot product. But it's exact. That's the point. It's exact. So if you can do it in 1D, a general problem, it's exact to use this. Only for 1D. There's only known solutions in 1D. And here's some simple experiments I did, that's the linear programming solution. The computational cost is the function of the size of the problem. This goes up more than quadratically, in fact, as a function. The green is the analytical solution. This is a zoom up here, 200, that's a size of 200 dot points in our PDF, and this is a 10 to the minus 4 of the computation. So we're down in this little corner here. And there's the green one, and that's the comparator Monge-Ampere solution, which is what the Enquist and co. have used. So it's blindingly obvious that if you use a one-dimensional analytical solution, you're home and hosed because it's an exact solution to this problem. But can we make use of that? I argue that we can, and I'm going to show you how to do it. Okay, so before I get there, the open question, as I mentioned, was how you make these things positive. Okay, so we won't go through the technical case, but to make something positive, you've got a wiggle like this. We want to fit the blue to the red. To make it positive, we could add a constant. People have done that. They've rejected that. There are problems with doing so, loss of convexivity. You can just take the absolute values. You could do that. There are problems with that. You could take like with like, which means you map the positive of the blue to the positive of the red, the negative of the blue to the negative of the red. You lose mass conservation, you get decorrelation associated with that. There's even a global strategy where you map the positive to the negative and the negative to the positive. People have tried every combination of these things. They all are somewhat lacking of any sort of general applicability and have problems. A great idea, a very interesting idea by Metivier and his group in 2018 was to turn this into a 2D problem. Rather than represent a waveform here in 1D, represent it as a point cloud in 2D. And that's something they call graph space OT. Now, I think that's a very interesting idea. In that case, you can get different mappings depending on what your choice of distance is, etc. I won't go into the details of this, but suffice it to say it's still an open issue. But this idea here is a sort of forerunner into the thing we're going to present, which is this one. So here's a waveform. It's actually a receiver function. And step one of the approach I'm going to propose here is to say, let's turn this wiggle into a two-dimensional image. And here's my two-dimensional image. I'm going to take all the points on the plane that are closest to any one point on the wiggle, on the seismogram, and call that the distance to the seismogram, the nearest distance of all the points on the seismogram. I'm going to associate that with a point on the plane. So I calculate a nearest distance field around the seismogram. So it's 0 on the seismogram and moves away. Now, seismologists will immediately recognize this calculation because it's exactly the same as wavefront propagation in a seismic model. Yeah? Very, very familiar. We're treating the seismogram as our wavefront and propagating it north and south at a constant velocity. So this is actually quite simple to do. Sethian introduced something called the fast marching method to do this. Nick Rawlinson exploited that in a series of papers and produced some nice ways of generalizing that. This is a very familiar calculation. So I'm going to go from 1D to 2D. And step 2 is going to be, well, in step 1 here, I've got a function which is 0 on the wavefront and increases away. And really, I'd like it the other way around here. I'd like it to be maximum on the wavefront and decrease away. So what do? The simplest thing to do is put it to a power of e. Take the exponential. So here's my PDF of my seismogram. It's a maximum on the seismogram, and because I've just simply taken the exponential and I've generalized it by putting it over a lambda, this is a fiddle factor. It's going to be my fiddle factor. I create a two-dimensional distribution around a wavefront. Now, I love these pictures. This is going to be my object that I'll compare between the observation and the synthetic. Now, I have to make a choice of a lambda, so there certainly is a fiddle factor there. But I told you that two-dimensional Wasserstein calculations are quite difficult, and I really would like to avoid them. So I'm now going to take a shortcut, and here's my shortcut. I want to compare this sort of fingerprint, I'm calling it a fingerprint, Fingerprints have been used multiple times in the geosciences recently. I think Hivoye used them in a paper. I think that looks like a fingerprint, so I'm going to claim the fingerprint space and call this my seismogram fingerprint. Here, it's just 2 Ricker wavelets. So comparing this to this, remember it's e to the power. I'm just going to take what we call the marginal. The marginal, I'm going to integrate that function over the amplitude to produce this blue curve here. So that's my observed, that's my predicted, and I'll integrate it in the opposite direction. That way's over time, integrating over amplitude this way to produce 2 marginals here. So now, I've taken it's an approximation, but I'm going to take, rather than comparing the entire 2D image, which is possible to do, it's just a bit slow, it's possible to do, I'm going to compare 2 one-dimensional Wassersteins. I'll calculate the Wasserstein between here and here and here and here and just add them together. Okay? So putting that all together, that has some big advantages in this because essentially a technical reason that the computational cost doesn't scale as a power of the size of the seismogram. It goes as n rather than n squared, essentially. So that's very nice because as these things get bigger and more complex, your thing hasn't run off and taken your entire computer budget. So this is very efficient. We put it all together. We have a set of boxes here. So we start off with an Earth model. Whatever problem you're dealing with, it produces a waveform. This is plug and play. You could put some other problem in here. These are the things we'd like to know from the waveform. Here's got our waveform. From our waveform, we get our fingerprint, which is actually a fast marching calculation, efficient, simple. From the fingerprint, we get our PDF, as shown here, which is, again, an analytical expression. And from here, we take the optimal transport between the observed PDF and the synthetic PDF. And that can be done very efficiently with the marginal idea I just described. Now, this is all fitting together. The whole point I've made these decisions is to fit them together to make them simple. I'm going to end with an example on this, just to show that it works, at least with our simple, a simple example that shows it works with this new concept of a PDF and a fingerprint. Now, here's my little fitting problem. I've just made this up just to illustrate the ideas, that's all. So I have a predicted, in this case it's a double Ricker wavelet. There's my predicted, that's the starting point. So this is time, amplitude, and here's my observed. And I want the blue to fit the orange. Well, it can change in time, of course. The blue can slide backwards and forwards, yeah? So that's a phase change or a shift. That's one way we can change this model. It could change in amplitude. Here it's a smaller one, that's another way, and it can change in frequency. So my 3 unknowns in this problem, in this simple little problem, are just frequency, amplitude, and time shift. And those are the sort of things that you need to fit to make a waveform fitting process work, yeah? But here I'm directly fitting them, so it's quite simple. So to give you an idea of least squares versus Wasserstein, on the top of this figure, I'm going to show an animation now, and we're going to slide the blue over the orange. And the middle, the red dot, is going to be, in the next pictures here, the 2 red dots is going to be where we are according to an L2 misfit, the least squares difference, and where we are according to the Wasserstein. You can see what's going to happen. As we slide one over, the L2 misfit gets better and worse and better and worse, of course, as things line up and get better and worse and better and worse. And that's what creates nonlinearity. That's called cycle skipping. It's a well-known problem in exploration geophysics, but also in fitting any high-frequency seismogram. So I've taken this example, I've sort of expanded it from one presented by Enquist and Flores in 2014. But you can see, beautifully, the Wasserstein distance is perfectly quadratic. Beauty. We can optimize this a lot easier than we can optimize that. In 1D, it's trivial, but you see the idea. So, let's turn it into 2D. This is the time shift we've just seen here for this fitting problem, and that's the amplitude. And this is the surface of the L2 misfit. And the red dash is the global minimum. So if we were doing this from an inversion point, we might have our 2 unknowns here, amplitude and time shift. We've got to jump over these barriers to find our way to the global minimum. And that's a classic multi-minimum optimization problem. That's where all the problems occur. All right? So what does the Wasserstein surface look like for this problem? And I said you could have the mass to the power of the distance to the power of p. So we're going to look at a p equals 1 and a p equals 2. What's the surface going to look like? Here we are. For p equals 2, it's perfectly quadratic for this problem. And for p equals 1, it's a simple linear surface here. On the bottom here, we've got our contours. And we can see, interestingly, that the global minimum of the quadratic surface is not exactly at, because there's noise in the problem, but it's very close to the true global minimum of the best fit, or of the true model. But all we seek is the global minimum. The global minimum of this is at the same point as the global minimum of that in this problem. So optimization procedures presumably will work much better. We're very encouraged by this. This is what we want to see. Turning a multi-minimid surface into a smooth quadratic surface. So let's try and optimize it. Well, skipping over very quickly, we can put this into an optimization framework. Anyone who's done this will say, but you've got to calculate derivatives. So it's worth just mentioning that in any optimization framework for this, with these our colored boxes again, it turns out that once we get to our waveform, what we want is the differential of the Wasserstein with respect to our model parameters, and we can stick that together using the standard chain rule. And the point is, all the hard work's done with my pencil and paper, working out the derivatives. Each of these derivatives are analytical. I'll say that again. Each of these derivatives are analytical. We don't have to do any calculation, no solving of a differential equation, no solving of an optimization problem. They're simple analytical expressions that we can plug in. Even I can code that up and put them together and calculate the derivatives of the endpoint, provided we have these first derivatives here, which depend upon the problem. We can put those together and get those derivatives. And just to show that that's working, here's that same example again. This is going to be our starting point, our blue waveform. The orange is going to be our target observed waveform. You can see it's off in time, it's off in amplitude, and of course it's off in frequency. And here, I'm going to play an animation. This is the Wasserstein distance as a function of iteration, and this one's going to be the equivalent least squares of the same model. So this is the path it's taking in the multi-minimid surface. But this is the one it's actually taking, because this is the one we're optimizing. And here we'll see how this one goes to fit this one. So we'll play it across, and what happens is, it's very quick, I realize that. It should play again. Okay, so what happens first is, all we're doing is rolling down this quadratic surface, but in terms of the fitting, the first thing that happens is the two waveforms line up. The second thing that happens is that their frequencies align, and the third thing is that the amplitudes align. And that's very interesting, I think, because when people want to fit waveforms or want to fit surface waves, the first thing they do manually is to try and align the envelopes, to try and align the energy, because we know that that's the best thing to do to try and fit the waveforms. What happens is this Wasserstein distance does that automatically, because that's where the biggest bang for buck is. Of course it is. That's what would happen if you could turn this into a globally quadratic surface, and that's what we're doing. So it fits the shift first, then it fits the frequencies, and then it fits the amplitudes. And you can see here that we're jumping over minima to global minima. So the least squares is getting bigger. That's because on the other surface it's jumping over them, whereas this one is going down uniformly. Okay, so I'm always telling my students, you can't present one result, everyone thinks it's a special case. We'll just do another one just for fun, because we've got time. Here's a starting problem where the initial wavefront has too high an amplitude, it has too high a period, too low a frequency, and it's shifted again. And we'll play the same thing again. Again, it fits the time shift first, and then it sort of does the amplitude and the frequencies together. Okay. So why do I think this is useful for the future? And it's because that this simple idea fits together, and we've produced a globally quadratic surface. Now that's music to the ears of anyone who fits waveforms. This is a very simple example. It's not yet clear that it will translate into more complex problems, but I am hopeful, with the fingers crossed, that it will. So again, this is for the students and the postdocs, that this is an interesting area that we could get into. These things fit together like a piece of jigsaw and produce a sort of system that seems to work. Okay, so my biased conclusions from my biased tour. There remain unexplored applications of sparsity. WUSA is experimenting with overcomplete tomography. There are other potential applications of that. I've really just given you a taster of that, but I think it's a step beyond what we can currently do with this concept, and we can generalize it. That's the idea. When machine learning obviously has great potential in inversion, I think everyone recognizes that. The real challenge is how do you actually make use of it? And we're suggesting that it's a surrogate for forward and inverse problems. Particularly, it could be used to replace or enhance Markov chain Monte Carlo or directly address nonlinear problems. Both of these are works in progress. There is potential. It's not the end of the story. That's why there's lots of opportunities to get into these fields. That's why we're forward-looking here. And I think building on the excellent work done in optimal transport, I think this is an exciting area. I mean, Andy Jackson got me into this, and I've not been able to think of much since, because I've always wanted to find a way of properly doing inversion. And I think this might be that proper way of doing them. And as always, these tools exist. These ideas exist, these little phenomena exist, and really the challenge for a geoscientist, and particularly the next generation, is to sort of be innovative in how you pose, how you bring these tools together. It's not plug and play. In all of these cases, it's a case of how you pose the question and how you might utilize these capabilities. And that's always been the challenge, I think. So I will finish with one last thank you and a comment on my life tour guides as opposed to my work tour guides. Those are the 4 people there. They're sitting in the audience. Without them, I wouldn't be here. They don't look like that anymore, but I think they look like that in my head. But I did say I was biased. Thank you.
Going live.
Well, thank you, Malcolm, for that wonderful lecture. Congratulations on being selected as the AGU 2020 Gutenberg Lecturer, as well as your EGU Gutenberg Medal, which is a very nice coincidence this year. Seismology President-elect Suzanne Vanderlee is also here, and she will be moderating the question and answers. So audience, please put your questions into the question and answer in the left. The default is you'll only be able to see your own questions, so don't worry, there are some questions there already. And the chat is public, but we won't be keeping track of that as closely. So yeah, Suzanne, go ahead.
Oh, well, thank you, Malcolm, for this wonderful, fascinating lecture and a vision to the future, and, you know, for harnessing data into more sparsely and precisely described models. So you've given us a lot to think about. I think this is echoed in the chat. There's a first question here already, and, well, there's a couple of questions. And so the first question from the audience is, can optimal transport be used to turn one velocity flow field into another?
Okay, so thank you, Anne. Thank you, Suzanne. Hopefully you can hear me. So
Yes.
Can it be used to turn one flow field into another? I would say yes, provided you're looking at a positive quantity. So it's a question of how you pose that problem. A flow field would be 3D or 2D, and I would say optimal transport certainly has problems just in terms of primarily in terms of computation, to work on 2D or 3D fields, but it's not impossible. It's the case of waiting for calculations to finish. But provided it's posed as a transform of one positive quantity into another, then yes, it can. And
So
next,
I guess, yeah, the next question, I'll go ahead. So, yeah, what do you think are the remaining biggest challenges in global seismology now that we have so much more data and inversion methods have improved so dramatically?
oh, good, a nice easy one. So, I mean, I think that data has grown dramatically, but is it ever enough? Do we know, how would we know that we have enough data to constrain the Earth at a particular scale? I think that is an unsolved question. So the big challenges, though, I think, are really combining data classes of different type. I mean, we're primarily seismologists here, and we deal with different classes of seismic data, but I think we need to combine that with other geophysical constraints from geodynamics, from surface geophysics, etc. So the combining of, and this is not a new challenge, it's one that people have thought about for a long time, combining data sets of different classes together. I mean, I'm hopeful on the optimal transport on that side as well, because really it's agnostic to the nature of the problem, provided you're dealing with things that can be represented as a probability distribution, and many things can, including three-dimensional objects. So there's a question, always a question of how you pose problems. But so I'm hopeful that this particular idea can be more broadly applied. But it's really only a case for highly nonlinear problems, I think, where we're in a linear regime, the standard methods work equally well. And perhaps a challenge, at least in respect to the optimal transport, is how you properly, how that might work with an adjoint style approach, because the colored boxes I put up there are really a replacement, or that they are the equivalent of an adjoint for a discrete problem. So properly integrating the idea of optimal transport with adjoint seismology, adjoint methods, I think there's some unknowns there as well. So I'd say that's a challenge.
Thank you.
So that's great, Malcolm. And if we can go back for a second to the first question and also what you answered in terms of looking at 3D velocities in 3 dimensions, what about just global tomographic models, for example? Right there, 2 days ago, there were presentations at this meeting about people creating a community 3-dimensional model by comparing a lot of individual global models based on certain types of data, but not other types of data. They're doing a great job comparing these data sets that the models are derived from. But what if one didn't have those data and just wanted to compare global tomographic models, right? Could you calculate this Wasserstein distance between 2 global tomographic models and basically find that a model with smooth low amplitude anomalies was actually very close to a model with more pronounced higher amplitude velocity anomalies than if you use a traditional sort of least square difference between every pixel in the model, for example? Right? Would this give you a better way to compare tomographic models more fairly?
I think that's an excellent idea. I would say the answer, I would guess, is yes, absolutely yes. But there's a big proviso there, because you will see that in the examples I chose, they're relatively small dimensional. So the linear programming approach will solve any of these problems, but maybe not in our lifetime, because the calculation wouldn't finish. If you look at the case, so my concern would be the number of discrete points or unknowns you have. We possibly need fundamentally new ways of solving the OT problems. And really, you're talking about a continuous field. So we're probably lacking in ways of implementing and solving those problems. But in principle, yes, they would provide a different distance measure, and one which is more, I would argue, is more suited to, or essentially provides a different look about how far away models are from each other. But that we would need a different generation of ability to solve the problem, to extend them to large 3D models. I don't see any immediate prospect of doing that, but it's an open question.
Well, there's a bunch of other questions, Malcolm. Thank you. So one here is wonderful talk and vision. For the Escher example to be like seismology, it disappeared. Oh, Anne, are you seeing the question?
Yeah, yeah, this is from Ed Garnero. Let's see. For the Escher example to be like seismology, we might need to dirty up some of the sparse examples to mimic poor data. Can you comment on identifying data quality for sparse sampling?
That's a good question. It's not something I've thought about, so I don't think I can give a particularly informed response. But for the sparse, I mean, the compressive sensing, the two constraints it has, or the two requirements, is one, randomized sampling, which we more or less have, and two, that you have incoherence between what mathematicians call incoherence between what you observe and where the underlying sparsity is, whether it be in the representation of the data or representation of the model. And that incoherence means that in terms of an inversion, it means every piece of data constrains as many of your unknowns as possible. The worst possible scenario is 1-to-1. If one datum constrained one unknown, sparsity constraints of compressive sensing do not work. It's the worst case scenario. The best case is when one unknown constrains as many as possible. But I mean, I haven't really answered Ed's question there, and that's because I don't really know the answer. But really, identifying data quality, it's more a case of more random, more spread out, the better. It doesn't really say much about noise on data, although people have done many sort of tests of compressive sensing and showed it's stable with respect to small amounts of noise. And all that really does is keep us comfortable that things don't blow up as soon as there's noise in the data. But I think there's certainly some open questions there.
Great, thank you.
Next question. Thank you for the great lecture. The misfit function using the Wasserstein distance seems smooth in the valley. Does that mean that the model resolution is lower? Is that the price we need to pay for a more stable inverse problem?
So I think not. I think that's just an illusion of the figures I showed. It's really that one gradient is so much higher than another. It doesn't actually say, I mean, it says something about relative resolution, relative sensitivity in that problem of the data to the particular unknown. And of course, it's most sensitive to the time shift. So they're the places where the curvature is highest. But even with the other parameters, it's still quadratic. So in that case, it's really about the global minima. There's nothing really about uncertainty of resolution in that. That's an unknown problem. If you take a Wasserstein approach, how do you transport our, to use the pun of the word, transport our notions of uncertainty into that space? And we don't know that either. So the simplest thing is to use things like optimal transport to find a solution, and then use linearized uncertainty analysis as normal. So it's not clear to me that just because of the shape of the Wasserstein, that means you've got more or less resolution in one parameter or another. That depends upon noise in the data.
So thank you. There's another question here. Is that says great talk. You showed an example for random sampling of two scales. Does it work if there are fractal orders of scales, like many geophysical problems do?
So you're talking about the overcomplete tomography there. Again, the short answer is I don't know the answer to that, but really you're looking for problems that are sparse in some sense. So that doesn't rule out a fractal distribution, but it means that you probably need to represent that in the right basis, and maybe there isn't any that converts that fractal Earth to something which has sparsity in some unknown bases. So the examples I showed really were to pick up the idea that you might have a long wavelength background to a model, and you might have much finer scale features, a subduction zone, for example, in a long wavelength Earth model. You're not necessarily, well, if you had a fractal distribution of structure in the model and your data is sensitive to it all, then there's no obvious way that the overcomplete tomography would work out of the box on that. You would need an appropriate basis in which is the weak point of all sparsity, as I pointed out. All we've really done there is convert, move the weakness one step away to try and allow multiple scale lengths, but they are still discrete scale lengths to be recovered in a model.
Excellent. There's another question here. It's about the Markov chain Monte Carlo approach, that it's largely limited to 1D and 2D, and very recently started to move on to 3-dimensional inverse problems. Do you think that your GAN would be better suited for 3D inversions?
That's a good question. So in the example I showed, the GAN is using the output of Markov chain Monte Carlo to try and replicate it. And once it's replicated it can generate samples extremely quickly, extremely cheaply, because it's not solving the forward problem. But the assumption is that the distribution of those samples follows what you've already discovered in your Markov chain. So it's not replacing it in that context. But I do think that one of the underlying hopes with things like neural networks and GANs is to perhaps train them on simple problems to expand to higher dimensional problems. So I think there is a hope for 3D and complex problems with this sort of approach. It may not be the one I just described, where you're using the output of MCMC to start off with. There is hope, at least, but I don't know of any evidence that it works, that this type of approach could be extended to larger dimensional models once something's trained, really, because once it's trained, the dimensionality doesn't matter.
Right. Well, then let's move on. Is there a standard way to incorporate the observational uncertainties in inversion using optimal transport?
That's a good question. I don't know of any yet. Well, as I said before, that the default position would be to use standard uncertainty measures and just use the Wasserstein for optimization. And once you've got a model, you've got a model. You can do linearized or uncertainty analysis about that. But that's no different from what we currently do. Whether it's a good question to ask whether you can do, whether the Wasserstein incorporates ideas of uncertainty. And it's something I've thought about, and I don't have a solution to it. But it's not clear to me if you could do that, you would get much more than what we currently have with linearized inversion around a solution. So certainly at the moment, I just see it as a replacement for the optimization part, not the uncertainty part.
Okay. And so the audience is coming up with these really good questions. Here's another one for you, Malcolm. Can optimal transport help compare observed seismograms with predictions from stochastic Earth models?
Well, I would say it's agnostic to where the waveforms come from. So, in principle, yes. Any waveform that can be converted, and again, I said that's the open question. I've converted it into a positive function one way, and others have done it other ways. And once it's in that form, absolutely, you can use the Wasserstein distance to compare the two. So I don't see there's any real problem in where those seismograms or receiver functions or any polynomial function comes from.
Okay, so can I add a question of my own?
Yeah.
Okay, I'll just do it then. I think there is a bit of a delay. So basically, in the beginning of your lecture, right, you mentioned that your lecture is primarily for students and postdocs, right? And so this past summer, seismology graduate students from around the world attended a summer school, right, where they got their feet wet, right, or wetter, in the intersection between data science and seismology. And do you think that a future summer school should move more in the direction of more data science and machine learning and optimal transport and inverse problems, or in the direction of more seismology, so that as a community or guild, we don't lose the art of extracting meaning from nearly every wiggle in a seismogram? Right? So the magic art of reading a seismogram
yeah.
and knowing what the wiggles mean and where they come from.
I'd say you need both. I mean, there's nothing. I'm not in the camp that we can replace seismologists with machines. No, absolutely not. You know, computer scientists have this term called domain knowledge, and they say, you know, and of course you need a bit of domain knowledge somewhere. And for me, domain knowledge is the key. I mean, that was really the point of my last slide, and saying that these sort of tools exist, but they exist in a sort of abstract sense, and it's really up to the informed seismologist to make use of them and to pose questions, as we've had in the chat here, ways of making use of them. It's about the question you ask. So I would absolutely say you need proper seismologists to be the leaders of these things, and be aware of and adopt the translation from other fields of these tools. I don't think one replaces the other, and they never will. At the same time, I mean, the volume of data is increasing, so I do think that we will be increasingly dependent, and therefore must be aware of these tools that come from other fields. And they are just tools. They're just concepts and tools. And optimal transport has actually been around for 150 years or so, and revamped in the last 50 years, and really it's only the last 10 or so that geophysicists seem to have heard about it. But so I'm a big favor of you cannot do away with the expertise of the discipline. Absolutely.
So I guess we're running out of time, so this will probably have to be our last question. This is probably not a short one, though. But what do you think will be the next steps? Should we review the models that we have?
Oh, the next steps of what?
I don't know.
Oh, yes.
The
Okay.
next steps of geophysical inversion.
Right. Look, I think we always review the models we've had. Yeah, as we add more data or we have new data types. I think the real challenge in global seismology is utilizing different classes of data. You know, I've been on the sidelines clapping a bit about using the correlation wave field in addition to the seismic wave field, and that because that provides different. It's in its infancy, but it provides different styles of constraint on the Earth. So I think the really exciting challenge is not necessarily, well, we always review the models we have. We try and update them with more constraint. But it goes back to incorporating different classes of data. And I think there's a mini revolution going on right now at both ends of seismology, in the ambient field and in the correlation wave field. And the future is obviously about bringing these things together. So I think the most exciting thing is finding new constraint in observations, I would say. And I think we're in an age now where that is strangely happened in more than one area of our field. And so the mistake would be that I've always used body waves, therefore I use body waves. I've always done surface waves, therefore I'll do surface waves. I think there is an argument of bringing different classes of data together in some sort of, which poses challenges for how you actually interpret and how you do the inversion. But I think that's where the future lies.
Well, thank you so much for your stimulating lecture. Thank you, attendees, for your attention and for all your great questions. Please enjoy the rest of the AGU meeting and take care.
Thank you.